Welcome to the Global Composites Experts webinar series. My name is Wenbin Yu, Director of the Composite Design and Manufacturing Hub. This webinar series is to examine the history, present capabilities, and future of composites, with the goal of sharing the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in this beautiful Indiana Manufacturing Institute. All of you are welcome to visit us when life returns to normal and it is safe for us to travel. We launched the CDM Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. CDM Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together. We envision CDM Hub to become the premier resource for composite design and manufacturing in the near future. This webinar series is one of the initiatives CDM Hub started as a service to the community. This webinar series is made available by the support of CDM Hub sponsors, including Dassault Systems, SciTech Survey, MAC Software, and Modex 3D. We greatly appreciate their financial support for CDM Hub. Next, I will show a brief commercial from one of our sponsors.
The Dassault Systems 3D Experience Education Center of Excellence in Advanced Composites is the result of a 7-year partnership between Purdue University and Dassault Systems. It is expected that this new level of engagement will bring significant benefits to the two partners and to the global society as we work together to bring the advantages of the digital age to society. Together, we will advance the digital enterprise by developing the human talent essential to this new paradigm and by utilizing the 3D Experience platform to exercise digital twins of complex composites manufacturing and performance to demonstrate the power for simulation of phenomena that are understood today only by empirical experiences. We will work together to introduce those concepts to a wide range of industries within the advanced composites community, from the original equipment manufacturers to the supply chain industries.
Thanks again for our sponsors' support. We invite more organizations to join them to serve the global composite community together. This webinar will be recorded and made available on CDM Hub. An email will be sent to you once the recorded video is available online. The presentation will last about 40 minutes and will have about 15 minutes for Q&A. All attendees are muted. Please submit your questions through the Q&A box. After the speaker's presentation, your questions will be read and answered.
Welcome, everyone. My name is Dianyun Zhang. I joined Purdue University last year, and I'm an assistant professor of the School of Aeronautics and Astronautics. Today, I'm honored to have the privilege to introduce our webinar speaker, Professor Byron Pipes. Professor Pipes is the Executive Director of the Composites Manufacturing and Simulation Center of Purdue University. He was elected to the National Academy of Engineering in 1987 and the Royal Society of Engineering Sciences of Sweden in 1995. In 2018, at the 150th anniversary of the founding of engineering in the United Kingdom, he was awarded the honorary doctorate honoris causa by the University of Edinburgh in Scotland. Dr. Pipes is recognized for his leadership in creating partnerships for university research with the private sector, government, and academia. He served as president of Rensselaer Polytechnic Institute from 1993 to 1998 and was provost and vice president for academic affairs at the University of Delaware from 1991 to 1993. He served as a Dean of College of Engineering and the Director of Delaware's Center for Composite Materials during 1977 to 1991. He was appointed the John Bray Distinguished Professor of Engineering at Purdue University in 2004. Dr. Pipes has made significant contributions to the field of composite materials since the 1970s. His recent research programs focus on composites manufacturing with emphasis on simulation and additive manufacturing to understand the influence of manufacturing process on the development of composites microstructure and the resulting implications upon structure performance. Now I will give it to Professor Byron Pipes.
I want to welcome everyone to this lecture today as a continuation of the Global Composites Experts webinar series that's been hosted by Wenbin Yu, the director of the Composites Design and Manufacturing Hub here at Purdue University. And I'm delighted to share a few ideas with you today about rheology of carbon fiber thermoplastic polymer composites. But I want to talk to you a bit from a point of view of how this happened, and along the way, who were mentors and who were colleagues that were involved in this work and how that all happened. I think you might find this quite interesting. Let me lay the ground, if I will, for you in terms of what I'd like to cover today. I start with my first mentor and then talk a bit about discovering rheology with my second mentor and a colleague to discuss fiber orientation and flow. Then moving on to the thermoplastic revolution, to the work in extensional viscosity, its motivation, the viscosity tensor development, key renewal times in my career with wonderful colleagues, work here at Purdue on prepreg platelet molding systems initiated by Boeing, and extrusion deposition additive manufacturing work that was really in response to some pioneering work that had gone on at Oak Ridge National Laboratory, and later to establish the Institute for Advanced Composites Manufacturing Innovation with the simulation technology area here at Purdue University. The first work in my introduction to composites began quite early. In 1969, I joined a company which is today Lockheed in Fort Worth, Texas, and I was challenged by who was my boss at that time, Dr. Jim Ashton, to solve this free edge problem that had been discussed because people were depending entirely upon laminated plate theory for much of our early work. It had just recently been developed and adopted to composite materials, and while laminate theory did provide a very excellent platform to understand these interesting anisotropic materials, it failed to explain what happened at the free edge. This free edge work, this challenge, if you will, had been offered up by the U.S. Air Force, and there was a gentleman there by the name of Nicholas Pagano, who also was working on this problem, and I was sent to meet him and talk to him at that time. And he and I met, we became collaborators, then he became my mentor, and the work that we published together in this area certainly launched my career. The interesting thing that happened is that Nick continued to follow this problem for another decade and developed the extraordinary understanding that we have today in terms of how stress transfer occurs at a discontinuity such as a free edge. He published much of this work in a book which was edited by J.N. Reddy, and I recommend it highly to you all. At the very bottom of the page is the first archival article that Nick and I published together. Without Nick, I certainly would not be where I sit today. This work was continued here at Purdue some years later by Jonathan Goodsell. We had solved only the tension, extensional deformation problem. We had not solved bending We had not solved thermal expansion, and we had not solved twisting. And in many ways, Jonathan put the finishing touches on this work. The complete family of solutions is now available in a publication by Jonathan in 2016. The first real mentor I had after I joined the academic world was Arthur B. Metzner. And it turns out that Arthur, better known as Art, well known in the field of rheology, was an extraordinary faculty member. He, in many ways, set the example to what the modern faculty member should be, a scholar, and yet one engineering foot, if you will, in the industry, trying to understand what are the issues that are barriers to technology development. And Art was a master at this. He also led one of the top-ranked chemical engineering departments in the country at that time at the University of Delaware. And he and I became friends, which was a big surprise to me. And in many ways, he chose to be my mentor. And I have to tell you, it was a wonderful lucky break for me. As I looked at his career and modeled my own after it, to be fair, I found a few things that I thought were particularly important. And it's his view of collaborators and mentors. And it's quoted here on this slide. So I'm going to just read it to you because I want you to think about it a bit. There were very few associates over the years, both in academia and industry, who were not important mentors to me, meaning his colleagues. And as the years went by, older mentors were replaced by equally important younger associates. The young mentors in the last decade of my career were no less important than the older people in the first. I must say that this has also happened to me in a very interesting way. The young people I've worked with, particularly in modern times, have been both mentors and collaborators, and it's been a very fruitful time for me. Art introduced me to dilute suspension rheology, which was in fact the dominant subject of that time. There were all kinds of issues about what happens to a liquid when you put particles inside it, whether they be spherical particles or ellipsoidal particles, namely fibers, or not. And as you look at the history of this subject, you realize that one of our notable scientists, Albert Einstein, actually studied the first, really wrote the first equation on measuring viscosity or predicting viscosity from the viscosity of the polymer and the sphere volume fraction. You can see the equation given. And really, in many ways, Einstein established the base of dilute suspension rheology of that time, which propagated itself for another 100 years or more, because much of the work that's been done in suspension rheology is dilute, and there's some good reasons for that. Now, as we began to look at fiber systems, and I was particularly interested in fiber composites, the particles that are involved in a liquid polymer during the state in which the forming is taking place, namely the molding steps, requires that there be an understanding between the fiber orientation and the fluid mechanics or the fluid flow characteristics. Perhaps the most classic piece of work that everyone has used since this first was started is Jeffrey's solution. Jeffrey wrote a set of equations for an isolated fiber in a fluid flow, and he predicted the rotational characteristics of that fiber, that is to say, the rotation rate. And you can see Jeffrey's equation here, which is expressed in terms of the deformation rate tensor, in this case planar. I've tried to make it simple for you, including the vorticity. Each of these terms describes the fluid dynamics in which the fiber finds itself. And the fiber is reacting to forces, the hydrodynamic forces in the case of water, which cause the motion of the fiber. This is the beginning point of all the work that we have today in fiber orientation and flow and the prediction of final fiber orientation in a molding simulation. Now I'd like to introduce Marcel Crochet, who happened to come to Delaware at the time I was there. That's a common mistake to put one institution in front of another, but he came to us from the Catholic University of Louvain at Art Metzner's suggestion. Marcel Crochet had been working in the flow of non-Newtonian fluids, and he was developing finite element methods, which at that time was a very new subject. Marcel came, he met with me and talked. We became good friends and colleagues at that time. It's interesting, just as a side note, to tell you that Marcel became the rector of the Catholic University Catholic University in Louvain, in Belgium, and so he went on into the upper administration of the university. So he was a man of many talents. At any rate, I had a student at the time by the name of Richard Givler, and we were struggling with the idea of how do we take this fiber orientation model and integrate it into a fluid mechanics system in which the geometry could be arbitrary. Well, finite element methods give you the ideal method to do that. And indeed, Marcel worked with my student. I even sent Givler to Belgium for 6 months, and we published this work in 1983. As you'll see in a moment, it was for fountain flow. We looked at single fibers in multiple positions in this flow, and you can see as the flow turns back on itself, for long aspect ratio fibers, that is to say 1,000, and with a initial position or initial orientation of pi/2, the fibers really don't change orientation state very much to the left. Now, if you shorten that fiber substantially, again, you're using the classical interaction here in Jeffrey's equation for single fibers that are not interacting with other fibers. Nonetheless, what you see is that the fiber begins to rotate. It both turns orientation, but it also rotates and turns. As you make the aspect ratio of the fiber shorter, you see this is enhanced significantly. So one of the things that comes out of integrating Jeffrey's equation and the dilute form into these kinds of models is you have fiber tumbling, which actually is not present when other fibers are interacting with one another, which is not obviously managed in Jeffrey's equation. One of the ideas that Givler developed was to take individual fibers at n/6 orientation initially and act as if they were bundles and thereby follow an orientation distribution function during the flow. This was the preceding idea to what is being developed, what has been developed today in the orientation tensor, which I'll discuss in a moment. Now I turn to the period in which I discovered thermoplastic polymers. I had worked for many years, as you know, in thermosets. Coming out of the conventional aerospace industry, it was an entirely thermoset composites technology. It was not thermoplastic. There were a lot of reasons why it wasn't, and I don't have time to go into them in great detail. But in 1981, things began to change, and a company by the name of ICI in England, ICI PLC, what it did at one time refer to Imperial Chemical Industries, was advancing the idea that a thermoplastic polymer, polyether-ether ketone, could be an answer to aerospace composites applications. There I met a man by the name of Neil Cogswell, who is an extraordinary individual. This is a portrait of Neil. a man who comes from the Royal Marines directly into ICI without actually the kinds of engineering training that we were used to encountering, but he taught himself the thermoplastic polymers and composites and became one of the finest scholars that I've interacted with, and is the author of Thermoplastic Aromatic Polymer Composites, something that we all see as a very important contribution to our field. I spent the summer of 1981 working with him. These thermoplastic polymers have emerged as being materials of quite substantial interest to us in the future because unlike thermosets in the conventional thermosets in aerospace, their cycle times are measured in minutes, where thermoset cycle times are measured in hours. So we can anticipate large increases in rate of production of these materials, and that's one of the primary objectives here. People also tout their ability to be recycled, and that's another subject that we could spend some time, but I will not today. While I was at the University of Delaware, there was a small company nearby by the name of E.I. DuPont de Nemours, not small at that time, a major company. And I encountered a few engineers there, and they asked me if I could help them work with stretch forming of composites. And I said, fibers don't stretch. It doesn't make any sense to try to stretch this material. Oh, they said, we have stretch broken fibers. And I said, I don't understand what that is. Well, we have a machine that in the early days of polyester fibers, we would put them through this machine and it would stretch break them in such a way that the feel of the polyester synthetic fiber had the feel of wool or cotton. That's what we were looking for in those days. Well, the machine works carbon fiber, so we've stretch broken carbon fiber, we've impregnated it, and lo and behold, you can indeed form it. You can see at the lower right a straight channel which has been stretch formed into a curved one. So it did work. The question to me that they were asking, can we anticipate, can we predict the forces necessary to carry out this stretch broken forming or stretch forming? And I had to think about this for a while. It was not a subject I had worked in before, but clearly they were talking about a stretch broken carbon yarn which was in the presence of a liquid polymer because they were at the melt temperature. And so the question then was, could you anticipate what that property would be? Well, obviously it would be a viscosity. And so I began to look at that problem by formulating it very much as we had formulated the unidirectional continuous fiber system. But here we had to think seriously about concentrated suspensions. We had fiber volume fractions that were 60%. Typically, dilute concentrations were down in the range of 5% or lower. And indeed, no one had worked at the level of 60% volume fraction in these suspensions before. So it presented an interesting idea, but a nice challenge. And of course, a typical engineer with a challenge simply looks at the kinetics or the kinematics or some mechanistic idea from which you can derive the response. In my case, I looked at these fibers, these broken fibers of length L and diameter D, which were separated and moving at relative velocities, which are shown on the right. And then the shearing stress in the liquid surrounding the fibers is pretty straightforward. It comes out of that observation and the, if you will, the arrangement of the fibers. And we do have to assume things like square array, hexagonal array, or rectangular array in the system, which of course are not true in the actual case, but they are true enough to identify the mechanisms of stress transfer. And so you can write the strain rate as a function of the polymer strain rate as a function of the extensional strain rate of the composite in terms of the fiber spacing and diameter. The fiber spacing is S, their diameter D, and a term kappa, which relates to the fiber volume fraction. There were two of us who had worked in this, and Bachelor had done it. A very famous fluid mechanician had actually studied this in the 70s. I was unaware of his work and didn't discover it till after I'd finished our own work. And it turns out that the two solutions were very similar. They produced viscosity predictions, both of which depended on the length to diameter squared, meaning if you have a length to diameter of 10, it scales your viscosity at 100. If it's 100, you can do the multiplication for yourself. It goes substantially high. And typically we have long aspect ratio fibers. We have aspect ratios of at least 1,000 if they're going to do a good, efficient load transfer. And so it became very clear that this viscosity term was predictable, but that it was going to be quite large. And the two publications that I call out are the ones that Bachelor did and our own publication summarized in a book that was edited by Advani. I'll mention Advani again in a moment. These fluids that we work with, when we put particles in them, they are no longer Newtonian fluids. They exhibit shear thinning characteristics. They exhibit temperature dependence, of course, that they had long before they were suspensions. And you can take this model with Curot and represent all of that, the shear thinning, the temperature dependence, and the like, and the recovery of the Newtonian viscosity at zero shear rate. If you do that, you can predict all of the anisotropic viscosities for such a liquid that contains collimated discontinuous fibers of length L in diameter D. The relationships are complex, but they are in fact analytic solutions to these properties, and they give us two extensional viscosities and two shearing viscosities that were developed earlier, with the idea that eta 2,2 and eta 3,3 were the same, and that 1,3 and 1,2 were the same. So there are actually three elongational viscosities and three shearing viscosities for such a fluid. If you take those equations and plot them, this happens to be for a specific polymer with a length to diameter ratio of 10,000. And you'll note that the eta 1,1, the viscosity in the elongational direction, is measured in the 10 to the 6th level, whereas the shearing viscosities are 10 to the 1st. The second elongational viscosity is a bit larger, but not much. So all of the other viscosities are relatively near that of the polymer, but the extensional viscosity, which means it gives some really interesting challenges in modeling flow with this class of materials, what we are now calling hyper concentrated systems. Well, I make a comment here and maybe take a moment and say, how did this all happen? Well, were it not for Metzner, Crochet, and Cogswell, it wouldn't have happened. But it did, and it does allow us to consider hyperfiber concentration. It allows us to predict all of the viscosity, shearing, and extensional. It gives us the shear rate characteristics and dependence and temperature. However, it's limited to collimated fiber systems. And so there needed to be more to come on this subject. By the way, this was generally completed in the decade of the 90s. Well, I stop now and take just a small detour and point out two other colleagues who became renewing colleagues. Some of you know I I spent some years in the administrative world, and when I returned, I found these young colleagues ready and able to work again with me, as I call it, at the bench. Connor O'Grady, whom you heard from on this lecture series, the Global Composites Expert Lecture Series. You heard from him on January 21st. His thesis was published in 1990. It's still the record, 425 pages, the largest doctoral dissertation published in my group. But Connor's gone on to be the head of engineering at the University of Edinburgh, roughly equivalent to our deanships here in America. And what an extraordinary foundation he laid in the area of forming, something that we worked together in the 1990s. After I returned from the presidency, I joined NASA Langley Research Center, and a young man arrived there with his wife. Both were on NRC fellowship, having come from Canada, from the University of British Columbia. Both were students of Anush Husartip. Anush is an old friend now, but I actually never met Anush at that time. I met him through Pascal, and I learned all of the extraordinary things that Anush has done in composites manufacturing and thermosets. And I must say that they are my teachers in this field as I moved to composites manufacturing. Pascal Hubert became my colleague and my teacher in this area. Today, he is a distinguished professor at mechanical engineering at McGill University, and it was a wonderful and has been a wonderful relationship for many years. Now, let me point to the young collaborators that I've had here at Purdue who have been, and you'll see in a moment, the extraordinary work that they have done. I point at this group because they're all my doctoral students, save two. Justin Hicks came to us from Australia, where he did his PhD at Melbourne Institute of Technology. Camilo Cano was my student at Akron University in Polymer engineering, and he joined us as a postdoctoral fellow here at Purdue for a while. The rest of my doctoral graduate students, some shared with Wenbin Yu, like Missouri, and others, and these are the young people that I've worked with for the last 17 years, and they have made significant contributions, as you're about to see. The first area that they worked that I want to, it isn't the first area they worked in, but it is an area that Boeing supported us for some time, in which we've made some very significant contributions, I think, these students, is in platelet molding materials. Here we take thermoplastic prepreg, we cut it into pieces, we call them platelets, and we then mold them into shape to make complex shapes. This gives you high fiber concentration, moldable material that cannot be made any other way. We can have fiber volume fractions of 60%. So the team that came together, Tony Faberlaro, Drew Sommer, Sergey Kravchenko, and Ben Dinos, formed a team. Each one of them had a piece of this problem. We're asking the question, can we make a very complex shape? Can we predict the microstructure from the forming? Can we take the microstructure, measure it, and can we then simulate that microstructure and predict its behavior in terms of performance? Well, the first question was, can we use the classic fiber orientation molding that was available by that time? You remember I had started some of this work in the 80s, and so had some really fine people, Chuck Tucker, Pham Tin, Suresh Advani, Tim Oswald. These are all people that were working in this field, and over a several decade period, they developed this methodology for injection molding primarily. It used Jeffrey's equation. But you recall I said Jeffrey's equation has this problem that the fibers tumble, and we know they do not tumble. So what was introduced was a diffusion term. That diffusion term stopped the rotational behavior as if we're interacting with other fibers with this diffusion term. It gave us slowed kinetics. The closure approximation was used to predict the fourth order tensor with a second order orientation tensor, and we have adopted a second order orientation tensor frankly as a basis of this work. However, while it's good for fluid mechanics, it's not as good for our solid mechanics field, where we need the fourth order in order to predict some of our mechanical properties. Anyway, these fluid simulations were Eulerian. This orientation tensor Aij, second order tensor, was treated as a continuous and smooth field variable, but the viscosity is isotropic and rate and temperature dependent. Isotropic viscosity is problematic for us because, as I demonstrated before, we have a highly anisotropic viscosity tensor in the real world. And further, as the viscosity, as the deformation occurs in the molding, viscosity should be responding to orientation state. So what happened was that we needed and we provided a new approach, something with an isotropic viscosity tensor, something where the viscosity itself was a function of the instantaneous fiber orientation, where there was no need for this diffusion term to restrict fiber rotation, where Lagrangian formulation was possible, and we could extract the orientation from the deformation of the element and trace fibers. So here's the nuts and bolts, if you will. We describe the orientation of the fiber in the same way that it's always been done, but we then map out trace fibers. We develop a constitutive relationship which is truly anisotropic, and you can see the tensor for viscosity and shear rate, and of course the pressure term. We have the ability to do orientation updating as a function of the deformation gradients. No fiber tumbling happens. More than that, we can incorporate the anisotropy of the fiber system, as is shown here in the lower right. This is the work of Anthony Farballaro, and his PhD topic was published in 2017. I go on to talk a little more detail about the viscous compliance and the viscous stiffness matrices expanded in this form. This gives us three independent constants: extensional viscosity and two shearing viscosities, and we do orientation averaging over volume averaging, rather, over orientation state. We get the form that you see there. In our work, we've proven that the eta 1, 2, and 2, 3 were equivalent, so you can see the reduced constitutive relationship in the lower right, in which we have the fourth order orientation tensor, and really only one viscosity term remains. The flow in this, using anisotropic viscosity, must also deal with incompressibility. And there are two options here: either the implicit methodology with a hybrid element, or the explicit methodology where we use relaxation and a finite bulk modulus. Both are possible. Both approaches are possible. Now, the first thing that happens in these platelet systems is we have to take them individually and consolidate them into a consolidated state. This is the work of Drew Sommer, a PhD student who just finished with us in 2018, is now at Oxford University in a postdoc. Anyway, we looked at taking these platelets into a random state, consolidating them, and once consolidated, that becomes the preform for molding. The interesting thing is that this has always been an initial value problem, and if you don't get the orientation state and all of the geometric issues correct at the beginning, you can't possibly predict what comes next. In Drew's work, we showed that as the consolidation process takes place, not only does orientation state itself change, but also the thickness of the platelet can change as much as 40% in some of the packing geometries in some regions of the preform. This preform then enters the mold, and we carry out a molding simulation for the pin bracket geometry. What you see here are molding results for the pin bracket, in which we have the prepreg platelet material. It is squeezed, if you will, at the molten state and pushed into the mold. And this simulation is based in the Simula product with a smooth particle hydrodynamic formulation and finite element methods. Next, this orientation state is mapped into the solid model for the performance characteristics. The question is, how well are these predictions working? And to do that, the next student worked on computer aided tomography analysis, and what you see here is a molding simulation on the left and a CAT scan on the right. It's not a simple process to do a CAT scan and still preserve the large scale dimensions in the system. And Ben was able to do that with a very interesting density gradient methodology that he applied in his doctoral dissertation of 2017. I think you would agree that the molding simulation and the CAT scan results show very good comparison. The question next is, can you take that orientation data and that geometric data of the microstructure and use it to predict the performance of the molded product? This is, of course, where we're going, because we want to make products faster. We want to replace aluminum and other metals in aircraft with these products. And by the way, they are flying today in the 787. We start with damage mechanics, and I'll not go through the details here. If you're familiar with the methodology, you recognize it. And if you're not, I suggest that you go read about it. It's a very interesting subject. Let us understand that if we take a simple coupon of this material, there's large-scale heterogeneity with respect to the platelets and their orientation state. On the left, we have the 3D image of a scanned coupon. On the right, we have the orientation in that coupon. Let's see if we can predict its behavior. Well, here's the simulation, and on the far right is the actual, far left is the actual sample. You can see where it was broken. On the right, you begin to see the damage index, and you begin to see the fracture pattern that's developing. It is, in fact, at the same location and in the same character as the observed physical experiment. Once we had completed that, we knew we had something that was very special. We now have the ability to predict from the microstructure all of the performance characteristics of a virtual laboratory, meaning you can carry out the ASTM standards in an entirely virtual environment. This is the work of Sergei Kravchenko. Sergei graduated in 2017 and stayed with us and worked for a few years. He's currently in England at Bristol on a postdoc, and he will take a faculty position at the University of British Columbia with Professor Porsutip in the fall. We're very proud of him and his work. I now want to turn to 3D printing. It was announced in my introduction that I've been working in this area, and this really was initiated by work at Oak Ridge National Laboratory and their invention there of this technology. And it's come an awful long way since 2015. We can make very large scale parts. The printing is a step followed by a machining step. If you've been to Las Vegas recently and seen the Las Vegas football stadium, In there is a 390-foot tower, torch tower, which is made by this method, by this machine, which is a Thermwood large-scale additive manufacturing machine. This work here at Purdue is to produce the digital twin of this extrusion deposition additive manufacturing. It involves an awful lot of rheological phenomena of fiber-filled systems because we're printing thermoplastic polymers that contain short carbon fibers, and we're printing them at concentrations up to 50% by volume. That tells me I need to finish. Anyway, let me quickly say that the physics-based simulation workflow is called additive 3D. It involves all of the various steps from residual stress to creep to shape change. And this technology is in our workflow here with material cards and machine cards, geometry, stress and deformation, heat transfer, polymer physics, the whole simulation. And as you can see, it involves the classic steps. I'll finish with just one demonstration to show you that the simulation produces the temperature during the manufacturing process, the degree of crystallinity, and the residual stresses that are built into the part as it is produced. A very exciting and interesting set of research, and the team members, Eduardo Barocio and Bastian Brinken, and their 2 doctoral degrees from here, they're the base of this work. Let me conclude by saying that my summary would be that mentors and collaborators have been very key to me and to my work, and I think it's true for all of us. It's also true that if one focuses and continues to focus in a thematic area, that more progress is made. And indeed, we've seen really improved results with time and technological developments, not the least of which is the computing technology in the finite element area. Understanding of these problems comes from commitment. And if you think about the impact of your work, your impact comes from all of the things above. And thank you very much for listening today. I'm delighted to have spent this time with you, and I look forward to your questions.
Dr. Pipes, thank you very much. We've certainly enjoyed the conversation and look forward now to discussing further with the question and answers. Let me begin where you concluded on the mentors and collaborators are key. You have seen education and engineering education from every perspective, from a student to working in industry to faculty, all the way to university administration. And you've chosen to emphasize mentorship here today. What do you see as coming in the future? And what counsel would you have for all of us in preparing for that future in engineering education and in the relationship between university and industry going forward?
Well, that's a big question, Jonathan. You've given me room for another 40-minute talk, I believe, with that question. I think it would be presumptuous of me to say that I know the answers to those questions completely. I don't. I will say this, that we do live in an interesting time where knowledge, as we have learned to convey it as academics, that idea is unchanged. What is changed about it is that it is so readily available today. I remember the first time I went to class and a student in the class brought information to the class that I did not have. Now that sounds routine, but if you think about the process of Google and the ability to search and find information on almost any topic by almost anyone, the idea of delivery of content is less important today than it was when I began to teach and when I was taught, where the professor had all of the information at his disposal, and of course course, there was more information in the library, but it wasn't easily accessible. And it was obviously not terribly accessed by the routine student. So our job in those years, the professor's job in those years, was to convey the information. Here it is, learn it, take it, master it, and so on. I think our goals today are more about understanding information and evaluating its use in the problem-solving world that we're in. I think we almost have too much information available to us, and any student can write a paper on almost any topic today without actually having learned much about it because it's so readily available. I mean, to say that they've read about it and received it and sent something back to us does not answer the question, do they know this? Have they managed to dig into it deeply? And so I think we as faculty have this challenge. How do we do that? How do we transform from idea conveyors to I would say, idea expanders? How do we help a student understand whether or not the answer to the question that they have is correct? Because I think they have access to hundreds of answers, and these answers will grow, not shrink. So the challenge to us in teaching is not so much to what have we conveyed this information, but have we helped them assess the value of it and the quality of it. And I do think that is in many ways the challenge of our time. I don't think that one is going to go away soon because the access to information is just too great. We are talking to students who are not at the same level of information sparsity as it was the case when we were taught. And I think that accelerates. So I've seen the trend occurring over and over again where a student will bring me an answer to a problem which is clearly wrong, and the student doesn't know it's wrong and cannot differentiate between that which is an answer derived from a search process and an answer derived from fundamental science that has been developed and tested against the laws of science, which is is a base of what we must do and we must teach more vigorously, I think is the right way to say it. Now, that's a very weak attempt at trying to answer that question, Jonathan, but it leads me to one more point I'd like to make, and I had this opportunity often in my life as an administrator to help the faculty think about changing what they did and how they did it. That's not easy, by the way, but as an administrator, you do have this need to continue to renew the institution that you're representing. And I often ask the faculty, are we teaching what we should be teaching? Are we teaching what we have taught and what we were taught? And that is the inclination that we all have, is to do that. Now, as knowledge increases, and it's growing at this enormous rate, how do we teach more, continuously more? It's not possible. So we have to stop teaching something and to start teaching something else, in the sense that we have typically a 4-year undergraduate degree time frame to deal with young people. What we pack in that 4 years is a foundation, certainly not their complete learning, as that was the idea of my generation, that they taught us everything we needed to know for the rest of our lives in 4 years. Well, we know that's far from the case today. We know that continuing education on everyone's part is a necessity, not an option anymore. But it does require us as faculty to think more about, what are we teaching that we need to teach? What aren't we teaching that we need to teach? and how do we renew that process? It's not nearly as robust as it needs to be, in my view, in terms of change. That, and I would also say, look, it is engagement with ideas that often requires something about touching. That is to say, looking and reading are not enough in learning. It's like trying to learn without vision. It's a sense that touching is required. So laboratories are much more important than we've been willing to admit. We're not admitting it because it's too expensive to do, but it needs to be less expensive. We need to do more of it, and I've certainly tried to do that in recent years. But I'm in a very special position. I have the luxury of being able to do it. Others don't. How do we do that? I put that on the table as an unanswered question, but I know we need to do it. It's not enough to just have an idea discussed, but not engage with it in some very tactical ways. Sorry, I gave too long an answer.
Let me follow that up with another question that I know you and I have spent time discussing, which is the role of modeling and simulation, both in education and then also your views on where that's going for us as an industry. Certainly, you've spent a lot of time thinking about that and in developing a vision for the Composites Manufacturing and Simulation Center. But if you talk to that in the context of both this talk and the comments you've just made.
Well, I think we're in a major transition period. I really do. The simulation power that we have access to is extraordinary. It really is. And yet, as we go out into the world and talk to people day to day about this, as you and I do, in terms of telling the world what's possible. First of all, the world doesn't know what's possible. And I'm talking about the engineering world. That so much has happened so soon that most of the world doesn't realize it, and much of the practicing world doesn't realize it. And part of that is because it's relatively expensive. It requires a specialist, and it's therefore too narrowly based. It's expensive to do. It's expensive for the human talent, and so a company will say, well, maybe I would like to do that, but I don't know how I add that to my portfolio in a way that works economically. And so the force to change requires an economic element as well. This has to get faster and more accessible across a wide range, and of course it is. If you look at what SolidWorks has done in geometric 3D modeling, I mean, it's transformed that whole arena, and there are many, many more. But still, the things that you and I can do in university today, we need to get that in the hands of the creative people of the world, because the economic impact of doing things virtually first and saving all those iterative steps, all that empiricism, all that intelligence that you can bring, simulation has to be there, and it has to be more active. And we also have to teach it, and we have to expose our students to it, that it is possible, that it is essential in solving really important problems of the future. There are two steps in my career that I made important choices. One was in '84 when I decided to work in composites manufacturing, because I saw that as the primary barrier to the expansion of this technology. And the other was to focus in simulation in these years. And I think that's both of those have been timely and correct. Now we have to turn the society in that direction as well.
Dr. Pipes, thank you very much. We're at the end of our hour. We've appreciated the opportunity to listen and learn from you. And again, to our attendees, we thank you for your attendance here today. We look forward to seeing you again. We'll note that the next webinar will be May 13th. Pascal Hubert, whom we've discussed briefly here today. Looking forward to more about sustainable manufacturing of composite materials.